Hello. Today we're going to talk about Topic 1, Section 12, Complex Numbers. So the first time you saw complex numbers, it was back in Algebra 2 with the quadratic formula, right? Solving a quadratic. So hopefully you remember how to do that by plugging those numbers in there. So let's see. You plug them in, you get this. I get a lot of times kids stop here with 5 plus or minus 1 over 2. Don't stop there, okay? Let's not do that, okay? Because that's just lazy, right? We can keep simplifying. So know that that breaks into two other numbers, right? And we can keep simplifying that. So then we get our answer 3 and 2, right? We feel pretty confident with those. All right, don't leave it like this again, please. All right, example 2 and example 3 was again solving using the quadratic formula. Now, here it says in terms of I, so we get some imaginary numbers. Hopefully you remember what that is. So we plug them in and we solve. Okay, so you get down to the square root of negative 64. The square root of 64 is 8, but the negative means that there's imaginary. So there's your answer there. Now for example 3, I would of course move things over and make it all equal 0. So I would do that first. And then I go about and I solve it and I work it all out. And hopefully you remember this from Algebra 2, right? I know it's been a while, but it's just plug and chug, okay? And then simplifying. And here notice I was able to divide the 2 out because both numbers were even, 6 and 8. If that had been a 5 and 8, then I wouldn't have been able to. I would have left it as just one big old fraction. Okay? Okay, so what made the last two problems different than the first problem? Well, they were imaginary. And how did we get imaginary? Well, imaginary is the square root of a negative. So, the discriminant, the part underneath the radical, is what tells you what kind of solution you're going to get. Okay, so again, you have your quadratic formula. B squared minus 4ac all over 2a. Now here, you want to, I just made that worse, didn't I? Okay, perfect. All right, so the part underneath the radical, okay, if that had been negative, then I would have gotten imaginary, just like I did in the last two. So if the discriminant is negative, then it's not going to have any real roots, which means your graph isn't going to have any x-intercepts. So like, let's see. If you remember this one on example 1, this quadratic meant that you had a parabola and the x-intercepts were 3 and 2. 1, 2, 3. So I know it goes here and here. And since it's positive, I know it's going to do that. That's what these x-intercepts are. It's when y is 0. Okay? When the y is 0. So here, when we don't have any real answers, I can't graph that. I can't graph negative 3 plus 4i on the real plane, okay, the Cartesian plane. Okay, so when it's no real roots, your graph is going to look like this. Your parabola is going to be above, or it can be below the x-axis. Okay? All right. Let's see. So I just wanted to explain that one. Okay, so this was like the first one, right? So we had it like that. And the second one, if the discriminant is 0, all right, well, think about what that does to my equation. You get negative b plus or minus 0 over 2a. Well, then there's no 0, or there's nothing over here. You don't have two separations. You only have one, negative b over 2a. Doesn't that look familiar? Yes? Remember that was the formula for the vertex of the parabola? Hopefully remember that. Okay, which means that's our vertex. So our parabola, the vertex is going to be on my x-axis. And I didn't, okay, you get the idea. It's supposed to be right there, one point touching the x-axis. Okay, now it can go up or it can go down. Okay, kind of depends on your graph. If the x is, the a value is positive or negative. Okay, hopefully that makes sense. All right, so let's see. What are the values of t for which the equation has no real solutions? So that means it's only going to have imaginary solutions. Well, the only time that's going to happen is when our discriminant, b squared minus 4ac, is negative. So when it's less than 0. Okay, so we plug things in. We get t squared minus 4ac is less than 0. So we get t squared, too many negatives. 16 is less than 0. I guess, no, technically I would factor this. That would probably make more sense. So then you get t is minus 4, t is plus 4, is less than 0. So remember, that's when, I would graph it on my number line. And then I'd plug in values to see if it works or not. Okay, because we know it's not going to be 0 at these. We don't want it to equal 0. So those negative 4 and 4 aren't going to work. So I'd plug in numbers around it. So like if I plug in 0, well, yeah, that's going to be less than that, right? This is t, this is t. So 0 is going to work. 1, 3, those are all going to work. But if I plug in 5, then suddenly I'm too large. So it's all these numbers. So the values of t for which the equation works and has no real solutions, all right, must be between negative 4 and 4. All right. So let's see, simplifying I. Imaginary stuff does a pretty cool trick. So hopefully this makes sense. The I is the square root of negative 1. And then notice the first thing we're doing is we're squaring it. Well, the opposite of square rooting is squaring. So those just cancel each other. Think of it like that. So you have negative 1. I squared is just negative 1. And you can think of I cubed as just I times I times I. Well, what happens when you have 2 of them? Oh yeah, you get negative 1. So I cubed is just negative I. And then I to the 4th is I. And so when you get 2, you get negative 1 times negative 1, or 1. So this is pretty cool to know that anytime you get 4 i's together, you get 1. Okay? So, how to remember that? Well, you get 4 i's to see one whole picture, right? Because there's 2 sides to every story, right? So my set of eyes and your set of eyes. 4 eyes to make 1. I know, it's dorky. I'm just really tired. No, that's just who I am. All right, so let's see. Keep it going. So I like to do, what if I had I to the 100? Well, isn't that just 25 groups of 4 i's, right? So really, if I have 100, it's just 1. And that's what's kind of nice to know about that trick. So like if I asked you I to the 362, all right, well, we know that I to the 360, that's a multiple of 4. And we just need 2 more i's after that. So here we get 1 times negative 1. All right, so that's kind of like a cool little pattern. All right, next one. So given this, okay, so this is writing for the real part and the imaginary part. I know, you couldn't have guessed that, I'm sure. So if you have your complex number, the real part is the part without the imaginary, so 3, it would be this part, and the imaginary part is the part in front of the I. So it's going to be that -2. All right. So for number 3, change my color. Oops, sorry. So we have Z is this complex number. Find the values if the real part is 2 and the imaginary part is 9. So the real part is 2. Well, what's the real part here? Well, any part that doesn't have an I. Well, that's got an I. This doesn't, and neither does this. So y squared plus 1 must equal 2. Y squared equals 1. So y must equal plus or minus 1, right? It could be negative. All right, then the imaginary part must be 9. Well, the part next to the I would be 3x. So 3x must equal 9, so x equals 3. There's your answers. All right, so here we want to find this part. Let's see. I think there's 2 ways to go about this. Personally, I think the easier way is to move this to the other side. So how do we get rid of it? Well, since it's multiplying, we need to divide. Okay, so now we have 4 plus 7i over 2 minus 3i. Okay, so I'll write that out. So a plus bi equals 4 plus 7i over 2 minus 3i. Well, now we can't have it that way, right? Because I is a radical, and we can't have that in the denominator. So we're going to multiply by its conjugate. Conjugates are great, but whatever we do to the bottom, we got to do to the top. So then just multiply them out. So let's see. We get a plus bi equals, what's that? 8, 12, and 14. I'm going to combine my like terms as I go because why not? 14 and 12 is 26i, and then it'd be 21i squared, which is negative 21. And then the denominator is just going to be 4 minus 9i squared, so plus 9. Hopefully you remember I times I is negative 1. Okay. So this just breaks down to, what is that? 8 minus 21 is negative 13 plus 26i all over 13. And we can even simplify that, so we get negative 1 plus 2i. All right, hopefully that makes sense. Why don't you pause it and try the next one? Okay, go. Okay, so hopefully you got the same answer. If not, you can always come see me. All right, example 6. For 2 complex numbers, show that this is true. So that little star means the conjugate. Okay, so I'm going to prove this by making z equal a plus bi, and I'm going to make w equal, let's do x plus y. Don't know why I did another w. X plus y, I. So let's do z plus w. So we're going to get a plus bi plus x plus yi, and then do the conjugate of that. It's going to be the conjugate of z, so a minus bi, plus the conjugate of w, which is x minus yi. So here, let's think about how we do the conjugate of this. This is a plus x, the real part, and then we have plus bi plus yi, the imaginary part. So if we're going to do the conjugate, remember all we're doing is just taking the opposite of that middle number. So that's really just doing a plus x plus the negative, oh, I guess I should have said minus instead, minus our bi plus yi. All right, so that's how we do the conjugate of that. So then this, we get a plus x minus bi plus yi, which, notice is what we have over here. We have a plus x minus bi minus yi. I said minus, didn't I? Oh my goodness, I don't know what I'm doing. Distribute the negative. Don't do what I just did. Then your theorem's wrong, or your proof's wrong. Okay. Example 7. So solving solving systems. So you can do this with substitution, elimination. Let's see. I think this might be pretty easy with substitution. So moving the 2i over. So let's see. In case you forgot, we're going to get z equals, I'm going to distribute that I too. So 3i minus, not distributing the 3. So wi minus 2i, and I'm going to plug that in. Oh, well, I can combine like terms. So I'm going to get I minus wi. That was a terrible I. It's not letting me take it back. Okay. Sorry, it's going to bother me. So then I can plug this, since that's z, I can plug that into both sides here. So you get 7i z, so I minus wi minus 1 equals 2, another z, so I minus wi plus 2w. And then I would just keep working it out. So 7i squared minus 7wi squared minus 7i equals 2i minus 2wi plus 4w. So negative 7 plus 7w minus 7i. Let's see, what can I combine? Nothing over here, I guess. Oh, this turned out to be more work than I wanted, but that's all right. Okay, so I'm going to get all my w's on one side and move my I to the other side. So move that 2i over and move that w over. So we're going to get negative 7 minus 9i, and then negative 2wi plus 4w, well, minus 7w, so negative 3w. Okay, so now what we want to do is we want to take out the w and divide it. So w is negative 7 minus 9i all over negative 2i minus 3. Ugh, this one's gross. I really don't want to keep going. All right, you get the idea. Then you can divide it out, and then you have what w is. Then you can plug it in and find out what z is. I know, it's a lot of work, but that's one way to do it. Okay? Okay, if you had finished it on Cogni, you would have gotten these as your answer. Okay, I just want to make sure you understood. Sometimes it is a long process, but it's all just that algebra. Okay, so here we want to write 2 plus 3i cubed in a plus bi form. So we do not just distribute that cubed because this is a plus sign and we know better, so we can do 2 plus 3i times 2 plus 3i times 2 plus 3i. All right, so we FOIL things out. We get 4, was that 6 plus 12i plus, ooh, no, minus 9, because we get the I squared. So 2 plus 3i, sorry, I'm going to take the shorthand here and try to do this quicker. So let's see, negative 10, negative 15, 9i, I believe, and then minus, what's that, 36? Why am I having trouble with this? That feels wrong. Okay, so then let's see, we get negative 46 plus 9i. All right, well, I really hope I did that right. I hope there was a nicer way to, I wish there was a way to check it. Oh, but there is. All right, so knowing your calculator is really going to be handy. Okay, so we want to plug in 2 plus 3i cubed. So I'm going to do my parentheses. 2 plus 3i is going to be seconds. And then, where is it? The decimal. You see that little I there? There you go. In parentheses, raise it to the third power. Bam! Negative 46 plus 9i. Oh, wasn't that handy? All right, so yes, that is how you do it algebraically, and then of course with your calculator. So I'd of course opt for my calculator, which is your section questions, is literally that, okay? So you can always test yourself algebraically, but really it just comes down to watching your signs, okay, and going slowly, trying not to rush through it. But I like the calculator, okay? And you have access to it on my exams. But remember, there is a section on the IB exam at the end of the year where you're going to have to do stuff algebraically. So just keep that in mind. So make sure you know how to do it algebraically. They probably won't ask you to do the fifth power. Okay. All right. Oh, I'm sorry. I meant to show you those answers. Ooh, too much. Okay, so those are the answers. Okay, so what about plotting them? Okay, it's pretty basic. Of course, you're not doing it on the Cartesian plane, which you're used to doing it on. This is the Argand plane. Okay, it's also called the complex plane. So, of course, your real numbers go left and right because I can run across real things, right? That makes sense. I can't run this way, so that's going to be imaginary. Okay? So, if we've got the point positive 2, negative 3i, well, the real is my x and the imaginary is my y. So you write it like your point is the real part, comma, the imaginary part. Oh my goodness, my pen is like awful right now. Okay, so real then imaginary. So this would be literally 2, negative 3. So we go over here, 1, 2, 1, 2, 3. That is where Z1 is. Okay? Now, negative 2 plus 3i is going to be over here. So negative 2. Is there. So that's Z2. Okay. Then plot W and W2. W2 is just imaginary, so 0 for the real. So that would be like 0 plus I. So 0, comma 1. So that's W1. And W2 is at negative I, so right there, W2. All right, so what's the relationship between Z and negative Z? All right, that would be two ways you can say this. Okay, you can say this by saying that negative Z is the image of Z rotated by 180 degrees. Okay, because right, what's the straight line? We went from one edge to the other, so that's 180 degrees. Or we can say negative z is the image of z after a reflection in the horizontal and the vertical. So think about it. You flipped this across the horizontal axis and then across the vertical. So you can either say it reflected in the horizontal and vertical axis, or it rotated by 180 degrees. Okay? All right, sketch 2. All right, example 2, sketch the graph of the complex number in the Argand plane, given that it's 4 units away from the origin and makes an angle of 45 degrees with the positive horizontal axis. That's a mouthful. Okay, so we want to graph it, and we want to graph that it's 4 units away from the origin, and I want a 45-degree angle with the horizontal axis, so the x-axis and the positive side. So I want to go this way and make 45 degrees. Okay, well, hopefully we remember that a 45, 45, 90, right? You've done this so many times. These are the same. So I can go 4 units to the right and 4 units up. Okay, and that's going to be my complex number on the Argand plane. We can do 4 units away and makes an angle of 45 degrees. Of course, now that I'm saying it, I'm realizing that we couldn't really go 4 units that way and 4 units up because that's longer. We want it to be 4 units away, so we're going to approximate, what would that be, around there, I believe? Okay, so we're going to make this 4. Okay, so I would read this, that when you say sketch, you're creating a diagram that has a general idea of the shape and proportions. Okay, so I don't need to have these tick marks. I just need to make sure that I've got this is 4 and this is 45 degrees. Okay, that's my plan here. Okay, so given that z is this, find the modulus of a complex number and the argument of a complex number. The modulus is just a fancy way of saying the distance. Okay, so the distance is the absolute value. Okay, so the absolute value of a complex number is the distance. All right, and the angle, or how long that vector is. And here, the angle is called the argument of a complex number. Okay, so let's do this. I like to visualize this, so I'm going to make a graph. So if I graph 1 plus 2i, I'm going to be here and then here. Okay, so I want to find this distance. Okay, so we'll just call that x. All right, well, I have a fancy little triangle here where this is 1 and this is 2. So we know that 1 squared plus 2 squared equals x squared. So x is just the square root of the sum of the squares of the coefficient. So you square those numbers, add them, and then take the square root. Okay, so here we're going to get the square root of 5. That is the modulus in this one. Okay, then let's see, we want to find the argument. So that's the angle that's made. So that's your theta. All right, so that theta, well, notice I know the opposite and the adjacent. Oh yeah, so tangent of the y over the x, what am I doing? Tangent of the angle, I'm trying to do the end, I'm jumping ahead. Tangent of the angle is opposite over adjacent. So y over x, or 2 over 1. Okay, the imaginary over the real part. So then to get the theta by itself, we do the arctangent of 2. And then I would just get out my calculator we do inverse tangent, so second tan, also called arctangent, is 1.107. 1.107 is theta. Now we usually represent it in degrees. Okay, so you want to make sure, oh, was I in degrees? Check your mode. I was not. I was in radians. So my answer would have been wrong. So we hit enter, and we're going to try that again. So the inverse tangent of 2 is actually, that makes more sense. Now my angle is 63.435. Ooh. 63.459, I believe. That's in degrees. This makes more sense. That doesn't, right? That's because I was in radians. Okay? So check your mode. Okay? This one is in degrees. Okay? We're going to stick to degrees. Okay? Unless otherwise noted. So here, let's see, there were some practice problems. I'll let you guys try these. I'll walk you through the first one. So the modulus is the distance. So you start with the square root of the square of those numbers. So 2 squared plus 3 squared. So this is the square root of 4 plus 9, or 13. That's for the modulus. So you do that for every single one. Then for your argument, you're going to take the, remember it's the tangent of the angle is your y part over your x, so the imaginary over your real, so 3 over 2. So here for the argument, all we really have to do is the inverse tan of 3 over 2. Okay? So that's what you're doing here. So practice those. Okay, I'm going to pause it. Okay, so this is what I got for the answers. If you have any questions, feel free to come and see me. All right, so that's all you need to know about complex numbers from 1.12.